Okay, so liquids, these particles are much closer together than the particles of gases. This means that they cannot be compressed or squeezed together. This makes liquids much more dense than gases. Liquid particles are held together by intermolecular forces, which could be like hydrogen bonding, those van der Waals forces, and dipole-dipole were the three we talked about. Fluids are substances that are capable of flowing from one place to another, and they will take the shape of their containers. These are liquids and gases. That is one of their similarities, is that they both can flow and they both will take the shape of their container. Their container can be as small as like a water bottle or as big as a classroom or anything that has any type of physical boundaries. So molecules within a liquid will be pulled in all directions equally, which is shown in diagram A, and this is because of the intermolecular forces. This creates a phenomenon called surface tension. This is the measure of the elastic force in the liquid's surface. This allows objects that are more dense than the liquid to float. This is also what causes water droplets to bend or kind of appear bubbled up on your windshield, or at least in here we did it where we dropped water drops on a penny. So this is like in a lake or a river, you can see sticks or leaves floating when they normally shouldn't. This is because they are trapped in this surface right here, and there's tension pulling on it so you can't quite break through. Evaporation and vaporization pretty much are the same thing. Vaporization is the process in which a liquid is converted to a gas. Evaporization is the conversion of a liquid to its vapor form, formed by the boiling temperature of the liquid, or below the boiling temperature of the liquid. This is what happens on a daily basis. If you just set a cup of water out, it will evaporate at room temperature, even though it's not boiling. Condensation then is the change of state from a gas to a liquid. And in order for molecules to escape into the gas state, there must be enough kinetic energy to overpower the intermolecular forces. So remember from yesterday, we talked about how this average kinetic energy means that some particles are moving faster or slower than the others. So the ones that are moving the fastest generally tend to have enough energy to move past or into that gas state, and it leaves behind the slower moving particles. All right, so remember, a sample of a liquid can have a range of kinetic energies, which we just kind of talked about. Only those molecules with enough kinetic energy to overpower the intermolecular forces will evaporate. This is assuming that there is no energy or heat source being applied to it currently. Molecules that are left behind will have a lower kinetic energy, which decreases the temperature of the liquid. We see this when we sweat. We know that sweating is your body's mechanism to cool itself down. So when you sweat, you produce a liquid on your skin, and those molecules in that liquid are moving relatively quickly and have the ability to evaporate, leaving behind the slower moving, therefore cooler particles, which allows your skin to cool down. Okay? Evaporation rates increase as energy or heat increases. So why does that make sense? In terms of kinetic energy and intermolecular force, explain why that makes sense. Why does evaporation rates increase as energy increases when you think of it in terms of kinetic energy and intermolecular forces? Daniela?
Because the kinetic energy increases as energy increases, like temperature increases.
Okay,
so
yep.
It makes them move more, and that makes evaporation. I don't know how to explain it. I have it in my head. I don't know how to
Okay,
explain it.
so far so good, but how do we get the intermolecular forces dealt with? I mean, I think we have a fairly decent grasp that you add more energy, you increase the kinetic energy of them. molecules or particles, but what does that have to do with the intermolecular forces? Why is that a big deal, or how does it influence the intermolecular forces? I'm not just to Daniela, but to anybody. So what do you need to have in order to break an intermolecular force? Energy. So if you add more energy, are you able to break more forces? Yes. So by increasing the amount of energy, there will be a greater amount of the liquid's molecules that have the necessary kinetic energy to escape the surface tension of the liquid. And in order to escape the surface, you need to be able to break those intermolecular bonds or forces. Good. All right, so vapor pressure. This is a measure of the pressure exerted by the vapor that forms above its liquid form in a sealed container. So the important thing here is that you are dealing with a sealed container. If it is not sealed, the vapor will just escape, and there will be no pressure. And so this is constant for a substance at a given temperature, and it will be based on the strength of the intermolecular forces. If you have a weak intermolecular force, it'll be very easy for those molecules to overcome those forces. So you will have a high vapor pressure and a high amount of evaporation. And then vice versa, if you have strong intermolecular forces, there will be a low vapor pressure and low evaporation. In a sealed system, an equilibrium between evaporation and condensation will occur. So we show this with this double arrow, is that they are in equilibrium, so that there is an equilibrium between the liquid state and the gaseous state. And this happens because as we get these gas molecules, what do those gas molecules do once they're released from the water? Do they stay in one spot? No, so they're bouncing all around. These collisions are not actually elastic, and we actually lose energy. So when those gas molecules lose energy, they're going to condense back to the liquid form. So there's this constant cycle of the liquid evaporating, becomes the gas molecules go crazy, bouncing against one another in the walls of the container. They lose energy, which cools them down, which means they will condense back to water, and so that is where we get our equilibrium from. Vapor pressure and temperature. VP, or vapor pressure, is dependent on temperature. The greater the number of molecules escaping to the gaseous form increases the vapor pressure. So generally we get more molecules turning to a gas when there's more heat or more energy applied. When we look at boiling point, this is the temperature at which the vapor pressure of the liquid is equal to the external pressure. Oftentimes this external pressure will be your atmospheric pressure. As a result, it can vary due to atmospheric pressure changes. Your average kinetic energy of the liquid increases as heat is added. I feel like I've said that like 18 times in the last 8 minutes. This in turn will increase vapor pressure. A point will eventually be reached where all the particles in the liquid have enough kinetic energy to overcome the intermolecular forces and vaporize. This is your boiling point of a substance, is when all of the particles will be heated to the same temperature and that they have the ability to vaporize. So if we look here, when we just have plain Jane evaporation, your vapor pressure will be less than the atmospheric pressure. We cannot form bubbles. What do bubbles indicate? Boiling. So then if they're not forming, we don't have boiling happening. However, there are some particles with enough energy to escape the liquid state. If we're boiling, the vapor pressure and the atmospheric pressure will be the same, and bubbles can form and rise and create the boiling sensation that we know. The normal boiling point is the temperature at which the vapor pressure of the liquid is equal to the standard atmospheric pressure of 760 millimeters of mercury. To figure out your normal boiling point, there's 3 different substances. The red, blue, and yellow all indicate different substances. You draw your line on your graph at that normalized pressure of 760 millimeters of mercury, and where they cross your boiling curve or your temperature curve here, and then you go down. And so the normal temperature, normal boiling point of this diethyl ether is about 35. I would have said 35 because I don't have as many markings. But do you understand how that is figured out? Okay, good. So when we look at the boiling point or the normal boiling point of water, we always say that that's 100 degrees Celsius. But if you actually test it, many samples of boiling water will boil at varying temperatures because of things that maybe are in the water, the different pressures. And so it's not uncommon to see boiling points of water at like 101 degrees Celsius or maybe even 102 degrees Celsius. And it all is dependent on the current pressure of where the boiling is being done. That's why we have this normalized standard of the 760 millimeters of mercury. So when we report that boiling point of water is 100 degrees Celsius, that is assuming you are at a pressure, an atmospheric pressure of 760 millimeters of mercury. Does that make sense? Okay, good. The last thing then is the boiling point will correlate with the strength of the intermolecular forces. So the higher the boiling point means the stronger the intermolecular forces. The lower the boiling point means those intermolecular forces are much weaker. Boiling point will also be affected by external pressure. Higher altitudes, that atmospheric pressure is lower. If you have a lower atmospheric pressure, you will also have a lower boiling point. This is why when you're in the mountains and you're camping or whatever and you're boiling your ramen noodles, it takes much longer to cook the noodles because your water is not as hot when it's boiling. Any questions?